So our final speaker for the day is Deepak Subramani. He's an assistant professor at the Department of Computational and Data Science at the Indian Institute of Science. He obtained his PhD in mechanical engineering and computing from MIT. And he did his bachelor's in mechanical engineering from IIT Madras. He works in the use of, extensively works in the use of MI and AL for geoscience application, aerospace system, uncertainty quantification, and optimal routing of autonomous vehicles. So today he's going to give a talk on machine learning and geoscience applications. Floor is yours, Deepak.
Thank you, Shashi, for inviting me and having me in this session. So I will start my talk on use of ML and AI for geoscience applications. Let's try to, I pitched it at slightly at the level of a student, right? So at the level of a graduate student. So if it is too simple for some of you, then I apologize. I'll try to go faster a little bit so that, it becomes less, but so that I know everybody is at the same level, I just need that, right? So that's the idea. So the geosciences, right? So the science of our Earth, geology, meteorology, oceanography, astronomy. The key characteristic of all these geoscience fields is that they have large spatial and temporal scales. So let us just take the example of oceanography to try to understand. So there are 7 equations, this we all know, right? So conservation of mass, momentum, energy, all of these things, we know that. But just take Bay of Bengal as an example. Just 2 million square kilometer area, average depth of 2 kilometer. And if I consider a grid of just 1 kilometer by 1 kilometer and just 100 vertical levels, right? So if I do that, then I'm looking at 10 to the 9 entries for one primitive variable, right? So let's just take U velocity. I need 10 to the 9 data points. So now UVW, then pressure, salinity, temperature, and the wave height, and density, all of these variables. Right? So we just put all of that together, right? So I'm looking at 10 to the 10 dimensional data, and this is just one time snapshot, right? So now if I need continuous temporal data, right? So and I need, let's say, data every hour, right? So I multiply this with 24 times 365, right? So that's just tremendous amounts of data, really big data that we need over here. And the question is this data even available, right? So do you really have, definitely you cannot put a thermocouple every of the grid point in the ocean or the atmosphere. That's impossible to do. So is the data even available? And so the answer is that, okay, there are some satellites, remote sensing products that give you temporally sparse, medium spatial coverage data. Then there are in situ data points, right? So like spatially sparse, temporally dense data, this is available. And today there are these big numerical models, right? So that solve these equations that I talk about using data assimilation and, creating initial and boundary conditions and creating a model output, right? So these are not observations, but these are model output, which somehow, right, so assimilates the sparse data that is available. In the end, what we are all really doing is like these 5 blind men looking at an elephant and trying to figure out, where this elephant is doing or what it is doing. That's pretty much what we are doing in the geosciences, right? So you have all these different sources of data. And the question really is, how do you put all of these things together, right? So what are the different ways in which you can do that? So there are typically 2 ways, right? So in which we do science, what we call as the traditional science, in which, you have small limited data and limited observations, and then you make new hypotheses and you test those hypotheses. And typically, right, so for those equations that I talk about, the computational science that I talk about, right, so these rules are known, right? So the rules of how the data is related are known, right? So something like F equal to MA is known. Then you have data of M and A, and then you are trying to find the answer F, right? So from this is what is known, right? So this is classical programming, traditional science, a way of doing things. Now in machine learning, the field of machine learning AI, what really happens is you have lots and lots of data, right? So you have MA, and somehow, let's say I know the force that is acting on it, right? So somehow I know that. And then I'm trying to discover the rule, right? So I'm trying to discover the rule, what relates all this data sets together, right? So what is that rule? And just feeding lots and lots of data, I hope to discover these rules through generic hypothesis, right? So not a specific hypothesis, but through generic hypothesis, which a neural network can do, a linear regression can do, a logistic regression can do, right? So that's the data science way of doing things. Now, this is known, right? So even our Newton found this rule F equal to ma with limited data and limit different hypotheses that was being tested. So all the heat transfer correlations that are there from ages, Nusselt number is Prandtl to the 1/3, Reynolds to the 1/3, Prandtl to the 1/3, all these things, right? So how did we come with those, right? So it's also limited data and then linear regression models, right? So that's how all of those also came to the forefront. So why is machine learning popular today, or why is data science popular today? It's mostly because, right, so from the end of 2000s, just 2010, like around 2010, there was availability of large databases, especially in the vision and language communities, which has labeled data, right? So the ImageNet, Stanford, Professor Fei Li's ImageNet data set, and the advent of GPUs and a few updates in the algorithm, right? So how the backpropagation worked, and small advances in the activation function and understanding of activation functions. And of course, lots and lots of data that was generated for socio-technical systems, right? So internet companies were generating a lot of data. So this, and these are real world data, right? So not model outputs, right? So these are real data that came into the being, and then that led to an application of regression and classification that was before this not as much as humans can do, right? So now today a computer can distinguish between pictures much better than humans can do with the power of convolutional neural networks, right? So that's what really propelled the data science. But our geoscience is not like that, right? So we don't have as much observational data, right? So we have our equation. So we are actually doing science with small data and big physics models, right? So that's what we are really doing. Our data is small compared to the problem that the inverse problem that we need to solve, but we have lots and lots of large physics model data, right? So that's what we have. So traditionally, right, so there are observationalists, right, who go out to the ocean, collect the data, make this hypothesis like Newton, right? So the traditional way of doing science. And then there are theoreticians who just look at the equations and then just say, okay, let me get rid of Coriolis, right? Let me get rid of advection term, and let me just look at inertia, all these things, right? So theoreticians do that. And then we as modelers come into the picture, where we combine observations and theory to come up with the machine learning models, etc., right? So that can then allow us to do combine the data and do the job, right? So of these different blind men looking at that elephant, right? Piecing that elephant together, right? So how can I piece the knowledge of how my ocean is behaving, how my atmosphere is behaving, right? So that's really the job that modelers we are doing. We need to combine our knowledge of physics, large physics models as a priori knowledge, and then observations, and then as a base in posterior estimate, we must come up with our estimates of the geoscience fields. So what is the scope of applying these AI ML techniques in the geoscience applications, right? So number one application is, of course, for outlier or novelty detection of data from observational platforms. So if you run a lot of observational platforms like Shell does, or like IMD does in India, then you can do outlier or novelty detection. Now, further, you can also identify locations to install a new observational platform that enable better predictions by data assimilation systems. So if you have a data assimilation system and you want to figure out where to collect the data, then ML techniques can be used there. And the most important thing where I think AI ML techniques can today work is to automate labor-intensive processes. And today I'm going to talk to you about our research, which does exactly that, right? So to automate labor-intensive processes, for example, extracting features from remote sensing products so that our physics models can work from that, right? So remote sensing data gives you sparse information. but you can extract features from that and feed that into PD solvers, right? So that then that can use that and then keep going from there. So this is, in my opinion, that is the #1 application of AI ML in the geoscience field. And of course, you can also use that for guidance of autonomous platforms. So if time allows, I will also talk about some of our work in dealing with AUVs, autonomous underwater vehicles, and reinforcement learning for autonomous underwater vehicles. And then, of course, you can also discover a nonlinear relationship between variables, whereas previously the observational scientists, right, so they relied heavily on developing linear relationships using linear regression techniques. But now, since you have nonlinear activation functions and neural networks, you can go ahead and discover nonlinear functions between the different observational data points. Now, it is good to know where to apply. At the same time, you must also know where you should be cautious of applying machine learning, right? So in the geoscience field. So the #1 mistake that I see many people do is to try to learn physics relationships using data from PD models that do not have that physics. I get a lot of papers for review, and one of the most flaws, right? So one of the most important flaws that almost majority of them seem to have is that they run PD models, then they say that, no, I have tremendous amounts of data. Let me try to understand the physics from this, right? So if your model did not have that turbulence to begin with, right? So you cannot learn that from just model data. Observational data is a different thing, right? So observational data is where you can use these machine learning techniques and discover physics, not model data. Another mistake which people do is they go and do a small observational study, and they get maybe data worth a few days, and then they say this data is not even enough to do a simple linear regression model. But they say, let me use an over-parameterized neural network. Let me try to develop a GAN. Let me try to do all these different things, and then that also will not work, right? So in the sense that you really need to be sure that you have high quality data, or you have to do some kind of data augmentation, regularization. And scope for doing regularization data augmentation is to use our physics prior as the regularizer, right? So not simply L2 norm, L1 norm, L half norm, right? So that's not what we should do. We should use physics-based regularizers, right? So that may work, but just application, right? So that probably will not be good. And there needs to be tremendous caution in blind replacement of CFD models, that is PD solution, with neural networks for sensitive applications, right? So if you really want to get the temperature accurate, right, extremely accurate, and you want to replace a CFD model with PD solutions, I would be very, very scared to do that, right? So treat it like biomedical applications, and you will be fine. Okay. So now let me shift gears, and in the next 30 minutes or so, talk to you about some of our recent research results that came out very recently. So I'm going to talk to you about the one of the processes that I said where ML and AI can really be useful, and that is to automate labor-intensive tasks. So I'm going to describe to you a deep learning algorithm that we have developed for ocean feature extraction, AI system for ocean feature extraction. So the background is that we have these data assimilative ocean forecasting models, right? So that require initial conditions, boundary conditions, and some synoptic features, right? So if you from the remote sensed image, if you know the features that are there in the ocean, for example, there is a current that goes, right? So western boundary current. There are these eddies that are present today, and I want to see how these eddies will evolve in the next week or so, right? So I need to initialize my model with the location of these eddies, and I need to make a prediction into the future for that. So estimation and detection of these eddies are very important, and traditionally it is done manually. It's a time-consuming task. Analyst looks at sea surface temperature image from satellite and observe, and also ask limited data that comes from fishermen, etc. Right? So that they do. Very limited automation exists today in operational data centers, in operational oceanography centers around the world. So there was a need to develop an automated physics-based data-driven synoptic feature detection system that was automated for these labor-intensive tasks, right? So further, right, so if you can detect these eddies, it is also good to issue potential fishing zone advisories, so that fishers can conservatively fish, right? So that they can do that. So the feature in focus today for us is the Gulf Stream and rings. So these are major ocean features in the Atlantic Ocean. This Gulf Stream is a warm and swift ocean current that originates around Gulf of Mexico, right? So somewhere here it originates, and then it goes around and comes to the coast of Europe. It governs the climate of both the continents, and it's an extremely important current, and making predictions of this Gulf Stream is an important task that people do. So Gulf Stream, it is caused by a large system of circular currents and powerful winds called an ocean gyre, right? So that's what causes this. So you can see, right, so in the sea surface temperature image, there is some signature, right? So this one over here, this is a signature of the Gulf Stream, right? So that's there, this is a signature. So how traditionally it happens is that a human, right, so looks at what you see on the top left, right? So this image is the sea surface temperature satellite image. This image that you see is the sea surface height satellite image. Right? So this is at a 5-kilometer resolution, and this is somewhere around 25-kilometer resolution. And a human analyst looks at these two images and draws something that is like this, right? So what you see here, this one is Jennifer Clark's Gulf Stream, a product that a person called Jennifer Clark, she's called as the Gulf Stream lady. She draws this out by hand, just looking at the sea surface temperature and height, and she has been doing that for maybe 25-30 years now, right? So that amount of data we have of human annotated figures. So what we needed to do was to somehow automate this process of a human analyst looking at it. So what we did was first create these maps of where Gulf Stream and rings were identified by Jennifer Clark. Right? So these maps here now give us annotations, and you can clearly see that, right? So if you're from the computer vision community, you can clearly see that this is basically a semantic segmentation task, right? So now given an input of SST and SSH, I must now get this guy out, right? So I must get the subfigure D out of A and B, and I need an algorithm to do that. So this need was there for a long time, right? So and classical methods of simple traditional computer vision have been applied, right? So threshold based edge detection technique, even a feed forward neural network without spatial information was tried. Dynamics based models with trying to calculate the vorticity, etc. All of these were tried with not too much success, right? So one of the critical challenges of threshold based methods was that it really depended on the season and months. You again needed a human to actually go and do that. Location of points of these oceanic features, they have spatial temporal dependency, they're intermittent features. And none of the ANN based techniques, the neural network based techniques, were not able to simultaneously detect these eddies and rings and the loops, right? So it was not possible to do that. But at the same time, right, so in the CNN literature, right, so convolutional neural networks were getting popular in the biomedical application, and from an input of natural images of horse riding, people walking, we were able to do semantic segmentation in that, and UNet architecture. This UNet architecture was developed for biomedical applications around 2015, and it seemed to do very well in the biomedical field, but it had not been applied for ocean feature extraction yet. So that's where we came in when we started our research. So we had data of SST, SSH, at different resolutions data was available, and we had the human annotation, right? So that is what we had. And now our task was to develop an architecture, neural network architecture, semantic segmentation network. This is what we wanted. And what we ended up doing was to develop a new architecture called WNet. So this WNet contains two UNet-like structures, right? So there is this encoder-decoder UNet structure 1, which is the SST unit. And then there is the SSH unit, right? So this is the SSH unit, and they combine together over here and give the final prediction of 4 labels, right? So Gulf Stream, warm eddies, cold eddies, and the background, right? So this is the 4 segments that they do. And then compared with the ground truth, a loss is defined, a cross entropy loss is defined, and this loss flows back in both the directions and updates the SST and the SSH part of the network separately, much like how a human analyst used to do this, right? So a human analyst would see the SST image first and draw out, and then use the SSH to make a correction. Or when the SSH images became available at 25-kilometer resolution, they started to have two separate experts who made their estimation of the Gulf Stream and rings from these two images, and then they merged it together, right? So that's how it was traditionally done. And so taking inspiration from that, we have this WNet architecture where there's a SST unit and a SSH unit that combine these together. Right, so the key properties are that there are different hyperparameters for both the units, right? So it need not be the same hyperparameters, and the cross entropy loss function flows to both sides so that the weights get updated, and there are skip layers also, right? So that some amount of regularization happens. So before we came to this network, we did do a lot of ablation study on different architectures. We started with a unit SST, right? So simple unit SST, simple unit SSH, and a 6-channel unit, right? So where SST and SSH both are given, and it's a unit that is developed. And we were estimating the accuracy of getting cold eddies, warm eddies, Gulf Stream, etc. And a lot of other architectures were done, and you can see several were added after the reviewers asked, right? So that's usually how these kind of research goes on. And then among all of these, right? So we really find that this WNet gives you the best accuracy for simultaneous detection of cold eddies, warm eddies, and Gulf Stream. So let's look at how the WNet gets trained, right? So what you see here, this is the SST, right? So this is the SST input, this is the SSH input, and this is the ground truth which the network is trying to learn. I will play the movie. What you see over here is epoch wise how the WNet is functioning, right? So for on a training on a test data point, on a training data point. Okay, so you can see how the WNet is trying to learn. The black is the background, green is the Gulf Stream that is trying to learn epoch wise, right? So this is the outcome that comes, and after running a few epochs, right? So the WNet is able to detect simultaneously the Gulf Stream, warm eddies, and cold eddies, and the accuracy gives a very good accuracy in testing, right? So we perform the testing in different months, right? So different seasons. So we have just one network, and we use it for different seasons. So in the winter months, right? So this is the kind of accuracy that you get, right? So still predicting the cold eddies seems to be tough, right? So especially because these cold eddies are smaller in size, and it's difficult to detect that even for a human, right? So it's difficult to do that. But the network is able to get the Gulf Stream accurately, the number of warm eddies and cold eddies, right? So both of them seem to be good. And this is the state of the art in predicting the length of the Gulf Stream and the meanders, right? So all of that was getting extremely well captured in winter months, in summer months, in fall, right? So in spring, all of these across years, it's able to get that, right? So these are test images. And of course, we were not satisfied, right? So with just saying that, okay, the network performs really well, we try to understand what happens within the network, right? So we look at what are the intermediate predictions that come. And you can really see here that, both SST and SSH side of the network, because the loss is flowing to both sides, right? So SST and SSH, both of them are really trying to learn all these three features. If I just use the SST, it is getting the Gulf Stream right, but the eddies it's missing. If I just use the SSH, it is getting the eddies, the Gulf Streams meanders is somewhat missing. And if I just combine these two together, right, so all of these get really picked up, and all the different channels of the outcome in the intermediate layers, you can really see which layer is learning what feature, right? So it's really powerful to understand that. In fact, it also makes sense, right? So because a convolutional layer is in fact doing a vorticity operation, right? So it's doing a diffusion calculation, right? So it's actually calculating grad of the temperature. or grad of the height. It is calculating that, and you can relate the vorticity to be d square h by d x square plus d square h by dy square, right? So it is indeed calculating vorticity somehow. So convolutional networks should be able to get these features fairly well, and that's what we are seeing. Not only in the train and test data that we had, even so this was completed in 2018 somewhat, and in production, right? So for 2019 images, still we get a very good agreement. In the Gulf Stream, the eddy is slightly less accurate than in the test images, but still we are getting good accuracy across months and across unseen data, right? Completely unseen data. Of course, with more data added to the unit, it can further be trained and improved, right? So that's one of the advantages. So in summary, we developed a WNet algorithm, right? A WNet architecture, a deep learning architecture for simultaneous detection of Gulf Stream and rings from SST and SSH imagery. This was a deep asymmetric double unit architecture, so we call it WNet architecture. We have upwards of 80% testing accuracy in whatever we see, and visually good segmentation for unseen data that the network has not seen. So the idea for us is to use this for automated feature detection, and once the Gulf Stream's position and the rings are known, we'll feed that into a PD model, right? So an ocean model, an operational ocean forecasting system, an ensemble model that runs, and use that to make predictions into the future, right? So that's the idea. Simultaneously, we are also working on replacing that architecture completely with the pure recurrent convolutional network framework, but that seems to not be as good as using a PD model, right? So of course, right, all the physics is there, and a deep RCNN, the data is just not there, right? So from 91 onwards, we have data. Every year, we have about 52 images every week, right? So it's not sufficient for training over parameterized neural network models, right? So that's the state there. So this is available in the IEEE transaction on geoscience and remote sensing. Okay, so that's where this got published. So Shashi, how are we doing on time? Do we have time for me to also look into some of the other results that we have, or?
I think, yeah, you can quickly go through some of the results.
Go through that, some of that. Okay. So some of the other applications of machine learning that we did was to discover nonlinear relationships. I mentioned that as one of the points there. And so discover nonlinear relationship between variables. So we were trying to use machine learning to estimate Asian elephants' habitat suitability. So you had these sparse data of where Asian elephants were, and you had remote sensing images of its habitat, like where the elevation and precipitation, weather data, all of this was available, vegetation. And we developed a random forest algorithm, machine learning algorithm, that then was able to predict or estimate suitable habitats for elephants. So this is training a random forest machine learning algorithm for solving a problem of identifying habitat suitability of elephants. So this is in general called SDM, species distribution model, and the state of the art in species distribution modeling is MaxEnt model, the maximum entropy model, which is nothing but a logistic regression model, right? So at the end of the day, and now we are trying to do these nonlinear models for that. So that was one result. The other result that I want to little bit more talk about today is this reinforcement learning for autonomous underwater vehicle routing. So let's talk about that problem in the remaining time that we have. So autonomous navigation is really important, right? So we all know we are in that field, right? So let's try to see the problem that we are trying to solve over here, right? So we want to navigate a robot from X naught position to X final, right? So from its initial position to the final desired goal in a strong, dynamic, and uncertain current. And we want to optimize the time taken, the energy used, maximize the safety, and maximize the amount of data that is collected, right? So that's the problem that we want to solve. So what you see over here, this is the velocity, is the background flow field of the environment in which the AUV is moving. And this G is a scalar reward in some sense, right? So it's the information content in the data, or you can think of it as a solar radiation field, which a surface vehicle must capture the solar energy and thereby reduce the net energy consumption, right? So it must spend more time in sunny regions as it travels, so that the time and energy is optimized appropriately, right? So this problem is of traveling from XO to XF in an environment that contains a velocity and a field that must be collected along the way. And the job for the AUV is to decide its policy, right? So it must know how to travel from X0 to XF in such an environment. So that's the goal. That's the problem. So we model this as a Markov decision process, right? So this is an MDP where the state space is discretized into a spatiotemporal grid world, 3D spatiotemporal grid world, where each state is indexed by X and time. And we have discretized action space, right? So you have heading. So for a AUV, if you assume a kinematic model, then what it has to make a choice is at what angle should it move and at what speed should it move, right? So basically, these are the two control variables it has, right? So that's the action space is discretized. And we use a one-step reward, right? So the agent gets a reward of minus delta t for every time step it spends without completing its goal. And then, of course, if it hits a obstacle along the way, it gets a very bad negative reward. And if it reaches the target, it gets a high positive reward. And this reinforcement learning agent, it's a MDP agent, it must learn from this. And there exists an exact solution that can be calculated using dynamic programming, right? So an exact optimal policy can be computed using dynamic programming. But dynamic programming is very expensive to solve for this very high dimensional spatiotemporal problem. And so we have two paths. One is to use an approximate reinforcement learning algorithm, right? So that solves it and uses the power of GPUs, right? So you have open AI Gym, IISc, all of these things that are available. So you can use off-the-shelf reinforcement learning algorithms. But what we really wanted to do was somehow get the exact solution, right? So use the dynamic programming. We have environment models. So we have models, so we can do model-based RL. So why do model-based RL at all when I can solve the dynamic programming exactly? But it is computationally expensive. That was because there are only CPU algorithms that are there. So what we ended up doing was to develop a GPU algorithm, an algorithm for solving the MDP on a graphical processing unit. So there are two phases for this solution, right? So one is to build the model. So that is the transition probabilities and the reward function from the environment model that is there. So once I have the environment model, I feed that a stochastic dynamic simulation of the environment. I feed that into the MDP. It learns the reward structure and the transition probabilities. And then I need to solve the MDP. So there are sparse value iteration algorithms on GPU that is already available. What was not available was to build the MDP on a GPU. So that's what we implemented using CUDA kernel. So we wrote our own CUDA kernels to implement that. And what you see over here again is an application. I'll just show the application. Actually, before I show the application, let me show you how these AUVs are deployed, right? So this was a C exercise that we completed in Mass Bay, right? So it's near Woodsole Oceanographic Institution, right? So what you can see over here is a Remus 600 AUV that is deployed with one of our algorithms inbuilt, right? So at the time of this experiment, we were using a level set based PD algorithm for optimal routing of these AUVs. So what you can see is how the AUV is launched, and it goes and it takes a dive at about 3 meters depth. It flies at 3 meters depth. So you'll see it dive now. Yeah, that's where it dived. Once it dives, right, so it is autopilot controlled, right? So it just goes by that. And the computer takes over based on our algorithms, right? So which was very scary at the beginning, right? So because all these things work well on computer, but what really happens in the field, and the operator of that AUV, right? So it's $1 million. It's a research project, right? So he was very good in allowing us to do these experiments. Luckily, nothing happened, right? So we were able to show that, using our algorithms, it was safe, and that the AUV did not hit some obstacle along the way and get lost, right? So it was all fine. So I'm just showing that to say how these kind of algorithms, once they are tested on the computer, are tested on the field. What I'm going to show next is only computer simulations, right? So we have not done the field testing yet. So here it's an idealized example, right? So again, the double gyre flow, right? So which is the western boundary currents, which is common currents in the Atlantic in that region. So the idealization of that flow is this double gyre flow, and we use our environment simulation system to make that. And we are planning a mission of a vehicle that is flying at 80 centimeters per second, right? So based on our experience, the max flow is around 200 centimeters per second. So that's really the challenge over here. So you might ask, why are you even doing this kind of research, right? So why can't you just use the algorithms like RRT, RRT star, which are there for ground vehicles? So the difference between ground vehicles and these AUVs is that in the autonomous underwater vehicles, the currents significantly affect how the vehicle move, right? So it's a small thing, and the currents and it's the speed at which it can go is only 80 centimeters per second at max, or 1 meter per second at max, right? So that's where those Remus vehicles fly, and that the field current around it can go up to 2 meters per second. So it really is an under-actuated system, right? So you cannot really operate it that well in that scenario. And so I'll quickly show an example of a net energy collection mission. So what you see here is, this is where the AUV in simulation, right? So this is where the AUV is released, and this is where it is going to. And so that's the star mark where it is going to. There are these obstacles that keep moving, right, left to right, it keeps moving. And this is cloud, right? So this is a cloud band that keeps moving to the left. And the job of the AUV is to reach the target in minimum time, as well as collect maximum energy, right? So minimize the energy also. So it's a multi-objective mission that it is doing. And we can see, so it learns, right? So the reinforcement learning agent, the MDP solution is obtained. And then it is simulated in 5,000 different scenarios. And you can see that the learned algorithm, right? So the learned policy, when we use that, all the agents tend to stay in the sunny regions as much as it can. It avoids the obstacles, and then it reaches the final location within the allowed time, such that it optimizes the policy that is used here. It optimizes the net energy consumption. That policy is obtained as a solution of the MDP, and it is obtained as a solution of the dynamic programming GPU algorithm. Before we did this, right, so it used to take days to compute the solution. With our optimized GPU algorithm, it takes a few minutes, right, to solve this the scale of problems, right? So 200 by 200 by 200 grid problems, right? So with that, I will stop and take any questions that are there.
Yeah, thanks a lot, Deepak. Very interesting talk. Questions. Yeah, you can, anyone who has question can type it in the window and I would read it out.
Yeah, so one more thing. I mean, I did not know what is the kind of research that you guys wanted to see. And seeing the previous talk, we also have done similar work, right? So we use a Bayesian GAN for doing super resolution of satellite images, right? To see surface temperature images. So that is also something that we have done. Then we have developed a non-intrusive polynomial chaos Gaussian mixture model. So I think the previous speaker mentioned that the PC data simulation scheme, the filtering scheme that he used, did not capture it, only worked for Gaussian scenarios. So we also have some recent results on using Gaussian mixture models to do that. Right, so that is also there. So it's available. All the papers are available on our website. Right, so if you are interested, do get in touch with me.
Yeah, so I hope Nikolai will visit us soon. And then, yeah, you can have this interaction in person.
Okay.
So there's a question from Case, which is, under which circumstances will the ML Gulf Stream be superior to Jennifer Clark's prediction?
When she's not there, right? So she's going to retire soon. So at that time, we will only have the ML prediction, right? Otherwise, the human prediction is the best.
So this was also my question, which was the model will get as good as the human expert, or it can there is something more that can be done.
Maybe, right? So, but how will you test whether it is correct or not, right? So that's the problem of the elephant, right? So it's a blind man looking at the elephant. You don't know what the ground truth is, right? So at the moment, we can only say what the human analyst is saying is the ground truth.
Yeah, but somewhere where you solve the inverse, where you have the Gulf Stream, and then you sort of say something about how SSH and the other two look like. But yeah.
Yeah, and also imaging technologies, if it improves, right, so then further things will improve, right? So one of the issues is that the SSH is at quarter degree resolution, right? So something like 25 kilometer, 27 kilometer is the resolution, and some of these eddies are smaller than that. So there is a imaging problem, right? So the image aperture, it cannot see smaller eddies than that. So one of the things that we tried to do for alleviating that problem was to use super resolution GANs or a Bayesian particle filter super resolution GAN to make the SSH also come to the same resolution as the SST. That seems to improve slightly, but not 100%, right? So we get about 80 odd percent. That's the accuracy that we get. Compared to if we assume that the human is the ground truth. So gold standard is human analyst here.
Yeah. So if there are other questions, I guess it would be interesting to give the context for the elephants. Why do we want to have this model for elephants? Because it might not be so obvious otherwise.
Okay. So maybe I can give a slight context in that. So human elephant conflict is a big deal in India, right? So every day, a lot of elephants, either elephants die or humans die, right? So because of this human elephant conflict. And these are just very recent news articles where farmers get trampled, and then there are inhuman ways in which farmlands are protected using electric fencing, and these poor elephants don't know that. And then there are these highway projects that go straight through elephant corridors, right? So all of these things. And then recently there was a movie in India by Sherni movie. So it kind of got us interested, and the student also got interested in looking at conservation, right? So how we can use ML for conservation? Can we use AI for social good? Right? So that was the question. So the kind of question that we were asking is, can we make a human elephant environment interaction model that will allow us to do science informed policy making? Right. So we want to give the policymakers a model that says that, you know what, if you do this kind of development here, this is the kind of interactions that will happen with the elephants. And if the elephant is aggressive, this is what the kind of deaths that you might see. And so please impose this policy there. So we wanted to try to see it as an agent-based model where you have human agents, elephant agents, and environment layers. And then try to see if a reinforcement learning solution or a Bayesian consensus solution can emerge out of it as a data-driven policy, which you can do. So as a first step of that, we needed a species distribution model for elephants. So that's where we use this random forest to do that. So I will show you a sneak peek into the agent-based model that we are developing. So this is a village in Western Ghats. And what you see, this is a movie. Yeah, it's a movie. So the black dots are humans, the red dots are elephants. So as time goes, the elephants and humans move, and these are like food for the elephant to eat. So you can change the number of humans, number of elephants, and how they interact with each other in this agent-based model, and then try to say impose policies. So and see for different aggressive breeds of elephants or male elephants that come, all of these things, right? So how they interact with each other. When humans move, when can you even make a prediction, right? So let's say that this data comes from real-time analytics, like Google Analytics, like so cell phone data of where these humans are. And then there is a project to tag these elephants that is ongoing simultaneously. So if we have all that data, we can have a real-time monitoring system using this ABM, right? So and make a Bayesian prediction of where you think human-elephant conflict can come, and then avoid it, right? So that's the overall research goal for us in that field.
Very interesting, Deepak. So if there are no further questions, I think I give